instance, if we have in a home, we have people living in a home and the CO2 concentration is too high, then we call an action and we ask the people to open a window. And if the action is achieved, then the window will be open. They are going to receive a score, basically. So we're focusing on that in residential buildings, while the second application is a dashboard, which is more tailored towards building operators, both in residential and commercial settings. And the third application, which is the one that I'm going to show you today, is the Office app. There is a short video that I'd like to show. I hope this is going to play. Not really sure. No, it's not playing. But so I'm going to share the link of this video, and you will be able to see it, but I can also just describe it, the experiment. So we're based on the concepts that experimental studies are shown that regular exposure to mild cold climate can increase energy expenditure, energy metabolism, resilience to thermal comfort due to climatization, and resilience, for instance, to cardiovascular disease and insulin level. So what we are developing in our office, we're setting an experimental dynamic indoor climate in which the temperature change during the day following a temperature pyramid, as you can see in the graph. So gradually cooler environments during the morning hours and warmer temperature during the afternoon. So the research previously conducted shown that being in the same temperature all day, indeed it might feel comfortable, but it's not necessarily healthy. And we already shown with some previous research that dynamic temperature profile is indeed not less comfortable. So it's perceived even more comfortable by our users. So together with this the dynamic temperature that we call temperature training, indeed, because we would like to train our users to get adjusted to these dynamic controls, we're also testing this experimental setting. And here we want to test the hypothesis that cool white lights with more blue during the morning make you more alert in the early time of the day, while warmer lights at the end of the day can improve better sleep-awake rhythm, so also improving alertness. And here we're also testing the hypothesis that warmer lights increase the perception of warmer environments, also under the thermal perspective, thus increasing the acceptability ranges of slightly cooler environments that, as you can imagine, will reduce the energy expenditure, also for heating. So the way we're collecting feedback from the users, as I mentioned, is through sensors and wearables. Our users will be able to provide feedback directly through the app, for instance, with a touch screen, but also all the biometrical data from the users are collected, for instance, skin temperature and movement. We set up like different areas in our office in which the dynamic controls are run and some areas in which they're not run. So we're going to have like control sample as well. So as I mentioned, this is just the setup of the design. We're now in a phase of collecting the data. I will be happy to discuss this further with anyone who is interested. Thanks.
Okay, thank you very much for another excellent presentation. I don't see any questions for you coming from the audience here, so I'll ask you one of my questions that I came around with. In relation to what you're planning to do, do you have some sort of a voting mechanism if people are, let's say, 20 or 30 people or more in an office? In the app that you have, do you have a voting mechanism to say what temperature level each one could be, wanted to have, 21, 18, 17, so that you allow some sort of a balance?
Well, for the moment, we're testing the temperature pyramids that we force as a rule in our BMS system. That is somehow mimicking the temperature pyramid. So we're not allowing the possibility to choose the temperature per se. But over time, we would also like to ask if they would like to have a slighter, cooler or warmer environment moving forward.
Okay, thank you very much. So now we'll go back to the first speaker, Yimin, who's going to be talking about exploring thermal comfort in immersive virtual environment. Yimin, welcome back.
Can you all see my screen?
Yeah, please go ahead.
All right, thank you. All right, so thank you very much. I'd like to use this time to share some progress about this project that is still ongoing. And on behalf of the project team, Tiancheng and myself will present those results today. And it's mainly concerned with the reliability of using immersive virtual environments for thermally related, either let's say intention, or hopefully later on we can use that for behavioral, or let's say safely, human building interactions in this particular case. So really, it's about exploring the reliability of immersive virtual environments. So we all know the challenge. I think most of you probably agree with me that during the design phase, we all probably hope that we would have a better tool to observe human building interactions, especially for things like thermally driven behaviors. We all know that immersive virtual environments are good for visual related studies, like studying the we use that for design validation, those sorts of things. But for studying thermally related aspect, we need an additional tool. So in this case, we find out that if we combine virtual environment and a climate chamber, that might be a good approach. So that's an opportunity there. But the question is, whether the user experience is different. So we use three different sort of parameters to measure user experience. We call it thermostat, but really we refer to sensation, comfort, and acceptability. And then we also use another parameter to perceive the temperature. That's basically the temperature around the person inside the chamber. And then the third is, of course, many people use physiological responses as well. These are the things like local skin temperature and heart rate. So here's the equipment and devices that we use. And the first is the climate chamber, and this is basically a office space, and we renovated with a very powerful HVAC system that you can control the humidity and the temperature. And then, of course, we use a heart rate sensor, and then skin temperature sensor, so forth. And then we use the HTC Vive as a way allow the participant to perceive the virtual environment. And in this particular case, the virtual environment is basically the interior of the chamber. And we also use the survey instruments to collect their thermal comfort, thermal sensation, acceptability, as well as some other data related to the VR experience, including the IPQ and the SSQ, and so forth. This is the procedure that we used. The procedure itself, as I mentioned, we are still in the data collection process. So that so the procedure itself actually helped us to collect more data than what I reported here. So by the way, this is not a thermal comfort study. It's basically, we want to compare IVE and in situ two settings. So in this case, we have two sort of exposures, right? So one is from 65 to 85, and the other is 85 to 65. We have three steps, 65, 75, and 85 Fahrenheit in this case. And then the setting is IVE and then in situ. And we also we also collect the data from two different contrasting outdoor conditions, especially the temperature, and we label it as a warmer and a cooler conditions. And then the last is that since we are comparing IV and the in situ, we clean the data based on the difference between the control temperature difference between IV and in situ, and the control is within 3 Fahrenheit degrees. And here are the things that the three hypotheses that we're testing. The first is, of course, we want to know the vote, right? The sensation vote, comfort vote, and the acceptability vote between IV and in situ at the three different steps. And the second is the control temperature. That is what the participant perceive, around that person. And the third is their physiological responses, skin temperature and the heart rate. And in this, we didn't, we have not yet, I should say, that study the heart rate and the skin temperature, for example, in the temporal scale. We use the average in this particular case. So I would consider this is still a very initial results. And we have used, we have 30 participants in this case, okay? And here are some of their the data about these participants. And for each of the hypotheses, there are different tests. So here I reported just the one case. In this case, you see the cooling in a colder condition, right? So the two sequences and each temperature, you see, we used a Fisher's exact because the sample is small in this case, less than one, of course, 1,000. That's what some literature suggests. So in this case, we used a Fisher's exact test, and the result is that none of the hypothesis is rejected. And the second hypothesis, we're testing their, in this case, we're looking at their surrounding temperature around that, the temperature around that participant. And, this is basically the distribution across the thermal sensation, but we also tested it using the thermal comfort and the thermal acceptability in a very similar way. And in this case, we noticed that there is no difference between IV and in situ in terms of temperature distribution as well. So none of the hypotheses were rejected, and the distribution, basically the perceived temperature around that person between IV and in situ was similar in this case. And here is the physiological responses. I only reported those are tested as significant. And you notice that most of the significant results are related to the forehead. And we have two cases that are different at different locations, neck and upper back. The forehead is most likely because of the wearing of the actual, the virtual goggle, the head-mounted display, and the upper back and the neck skin. At this moment, we don't have a very clear explanation to that. We also did some analysis at each site, and we couldn't find a very specific, because on those tests we don't see that particular differences. So we don't have a very obvious answer to those two sites.
Okay, you need to conclude now, please.
Yes, so this is the last slide. So based on the test of the data that we have, we at this moment think that there's a good potential that we can use IV, especially using those parameters as a good indicator for their in situ settings. And here are some of the future studies that I think we should do, especially I think at that moment, we right now we're doing sample-wide analysis, but I think we also need to look into individual different cases at an individual level, and several others. If you're interested, we can further discuss. Thank you.
Okay, thank you. Thank you very much. We have one question from the floor, and that's from Gary Rowe. It's got 7 votes. It says the in situ environment was also a false environment in the sense that it was not the subject normal working environment.
No.
Do you have plans to compare VR with real environments?
Yeah, that's true. I mean, at this moment, it is a very, it's a simulated environment. It's basically the environment, the chamber. But we do. I mean, one thing that I'm thinking about that probably we can do is to simulate another. Probably, for example, there are other places where people can have real sort of real labs, right? So like the lobster lab, you know, lab, something like that. And if we could simulate the lab environment like that, and then collect actual data from the actual lab and compare with a virtual environment in a chamber, so I think this will bring the result to a different will bring a different aspect to this particular study.
Okay, well, thanks very much. We have plenty of time at the end of the session for more questions and answers. And we are now moving into the quick presentation session of 3 minutes each. And I think we may have only one no-show in that session. Let's just see if this person will turn up or not. But the next presentation will be for 3 minutes. And it's by Matteo Favero, Energy Flexibility of Buildings, Understanding How Thermal Acceptability Can Enable Demand Response Strategies. Matteo?
Yeah, welcome everybody. My name is Matteo Favero. I'm a PhD candidate at NTNU, and today I will present an experiment, part of a doctoral thesis that simulate how often setting in a ramp-induced thermal environment. Before proceeding with the description of the experiment, it's important to give some definition. For example, in ISO 7730 and ASHRAE 55, they define ramps in the same way, a monotonic, not cyclic change in operative temperature of an enclosed space. The difference between the two is in the limit. Since ASHRAE specify more detailed limits, we'll use them as a reference for the ramp. As a starting condition, we select the category B with an operative temperature of 22 degrees Celsius and a maximum mean air velocity of 0.16 meters per second. Here you can see the facility that is composed of 2 independent cells of 10 square meters each, where both indoor and outdoor parameters were monitored. Outdoor parameters like temperature, global solar radiance, and precipitation were measured with 2 weather stations, one on the roof and one on the ground, while other indoor parameters like CO2 concentration, illuminance, and temperature were measured at different heights. This is a 4-month study with 40 subjects that participate for 4 or 2 full days. The day is a standard Norwegian workday, meaning 7 hours plus half-hour lunch break. There was a 30-minute acclimatization period and then the experiment, where the subject evaluated the indoor environment throughout questionnaire. The participants were also asked to press a button as soon as they felt uncomfortable, where uncomfortable was defined as taking action to restore the comfort condition. For example, if too warm environment, then regulate the thermostat or open the window. There were 4 types of questionnaire: an entry questionnaire with general information about participant, a subjective judgment scale questionnaire, a subjective judgment scale questionnaire plus a discomfort event, and an exit questionnaire with the final workplace satisfaction. Here you can see the thermal ramps for both cell A and B. where 172 for cell A and 181 for cell B. The discomfort thermal event, that are the dots in the chart, were 117 for cell A and 136 for cell B. Sadly, due to a lack of cooling power, we do not manage to have the steepest negative ramp. Here you can see only the thermal discomfort event for both cell A and B. The black squares are the Ashray comfort limit, and the dashed gray line is the fitted line between this limit. You can see that the discomfort events are not symmetrical. Subjects are more sensitive to cold variation than a warm one. In fact, 94% of the discomfort events for cold are within the comfort limit, while for the warm side, only the 48% are. To analyze participant thermal sensation and acceptability, a multi-level for logistic modeling will be used, while to model the discomfort event, a survival analysis has been selected. And after the analysis of this collected data, it will be possible to understand the limits of human thermal acceptability under different temperature variation before voluntary adaptation mechanism or action are taken. Thank you very much for your attention.
Thank you very much for being on time and so forth. So we go now, as can I ask all the speakers to please stay online so that we can have a discussion at the end of the session. So the next presentation is by Michael Kane, who is Occupant-Centric Control with Personalized and Contextual Thermal Comfort Behavior Dynamic Predictions. Michael? We can't hear you. You need to, that's it.
There we go. Thank you. Thank you for this opportunity to present our work on occupant-centric thermal comfort control. I'm an assistant professor at Northeastern University, and this work is in collaboration with my student, Kunal Sharma. This work is powered by data from 100,000 thermostats across the world, thanks to thermostat manufacturer Ecobee. So this work is motivated by existing occupant dissatisfaction with building control systems, that this dissatisfaction is exacerbated by our desire as engineers to have the buildings provide grid services. Occupants often don't understand and aren't motivated to learn the competing interests between thermal comfort and the grid trying to shed, shift, or modulate loads by controlling the HVAC system. We consider thermal comfort behavior dynamics as the amount of time it takes an occupant to notice their dissatisfaction with a set point change and eventually override it. So similar to the last presenter's work. This figure shows the result from 10,000 plus set point changes in the Ecobee data set. We can see here that as occupants are more uncomfortable, they are quicker to override the set point changes, kind of an obvious fact, but we have some data to show it from a large scale study. So how does this affect our performance, or can we predict this? From the work of many of you participating in the Annex, we know that occupant behavior is driven by both contextual and personal factors. So can we pass observation of these factors to predict if an override will occur, and if so, when? To predict if an override will occur, we tested both a decision tree model and a shallow neural network. We also tested to see if contextual factors were sufficient or whether we needed personal factors. The neural network was ultimately able to predict if an override will occur with 70% accuracy, while only 40% for the decision tree. Kind of highlighting the nonlinear effects going on here in this relationship. The results also showed that personalization does improve predictive performance. Here we compare approaches to predict when an override will occur, if we've decided that one will occur. First, we consider a simple model without contextual or personal factors, and we have a root mean squared error of 150 minutes for overrides that occur within 4 hours, so pretty significant uncertainty. The decision tree model is even worse at that than the population level model. But the neural network model is able to reduce this error by a half hour. Certainly there's still a large amount of uncertainty, but even with this large amount of uncertainty, can we build predictive controllers for flexible buildings? So the simplest form of load flexibility is demand shedding, where a thermostat is set back to conserve energy. And reliability is the name of the game in controlling the electric grid. So occupant overrides need to be able to be predicted. And currently we do not. Currently we use the same demand response kind of schedules for the entire population. So if we don't consider overrides at all, we modeled that this figure on the left here that shows kind of for a given setback and a given setback duration, what sort of level of curtailment. But if we then include the overrides, we get errors of over 100%. These errors can be reduced by using these personalized setback durations driven by the predictive model. This analysis is complicated by factors like the temperature is not always at the set point at the time that the setback occurs, and that in about 40% of the time, occupants overrode, but they overrode in a direction to further conserve energy. So there's some peculiarities with the data, but I think there's also peculiarities with human behavior. And we really have to try to understand of how good is good enough. I don't think we need perfect models here. We just need better models. So thank you for listening, and thank you to my grad students, Gunit and Chris, who have been working hard with this large ECCD data set. So I guess we can take questions at the end.
Yeah, thanks very much. I think there will be ample time for questions at the end, and I'd like to ask the audience to make sure they have questions, especially to those 3 minutes presentations, as they have not been asked any questions before. So do we have the 6th speaker around, or shall we move to the last one? Coordinator, moderator?
Please move on to the next one, if that's okay. Okay,
we'll move to the last presentation, and that's by Fillipo Vittori, and that's on on dimensional comfort, multi-parametric experimental experiment with a BIM design virtual environment.
Okay.
Fillipo, are you there?
Yes.
Please go ahead and share your screen and carry on.
Good morning to everyone. I'm Filippo Vittori, PhD student in Energy and Sustainable Development at the University of Perugia. Today, I will show you the follow-up of my master thesis, followed by Professor Anna Laura Pisello and Dr. Ilaria Piautile. The purpose of the work is try to find an integrated methodology able to stimulate placebo effect in terms of thermal perceived sensation. By coupling immersive virtual environment and BIM platforms, the target of the experiment is to study an easy and inexpensive method able to predict multidimensional and multi-physical comfort in the early stage of the design process. The procedure is made up of 3 main phases: concept, validation, and experimental phase. The first phase has been useful to understand a productive workflow to use and validate the means needed. In this case, it's user advisor to submit the virtual environment to the subject. In the second phase, asking to 50 people a judgment in terms of sense of presence on a 5-point scale, 2 environments are compared. On the left, it's possible to observe the first scene showed inside the visor, a spherical photo of a real office room, and on the right, it's virtual reproduction. The distribution of the sample is showed in this slide, and even if a little portion of the sample expressed the lower sensation of visual comfort during the submission of the virtual environment, the obtained results, otherwise the 17% of positive answers in terms of sense of presence, allowed to carry on the main phase of the procedure, the experiment, that is conducted over a sample of 100 people. In this case, the temperature is controlled and the subject perceived thermal sensation is asked on a 5-point scale. The quadruple variation of 3 parameters generated 12 scenes. The first variation has involved the aspect ratio of the window. The second variation, the window coating. And the last, the color temperature of lighting fixtures. Also in this case, the sample analyzed is as heterogeneous as possible, and a final observation of the collected data allow to affirm that the methodology is able of giving a placebo stimuli in terms of thermal sensation, considering separately male and female boats, but also these summary charts, in which it's possible to observe and to appreciate the global trend for each block. The following steps will include further monitoring to understand the role of cognitive bias in the process and try to find the new triggers able to stimulate the subjects. Thank you for your attention.
Okay, well, thank you very much for your presentation. I think we are now on time at the end of the session, in spite of the fact that we have one missing presenter, so we are within that time. So we'll start by having a discussion, but before we do that, I have some specific questions to specific presenters. And the first one is for Sarah Crosby. And the question is that how many human participants do you have in your study?
We have two different studies. For the copy study that we have used, the old data set, we had 779 person tested. And for the UBC study that we have, like the recent study, we had 150.
Okay. That's really good. And I think the next one is to Dr. Kane, and the first one is from the floor, not from me. I have one or two from me. What variables did you feed into your predictive models, decision tree, ANN, etc.?
Yeah, so I think that this figure here, I just shared my screen. So just shows that I think there were 30 some variables split between contextual and personal. So the contextual ones are kind of the obvious humidity, set point changes, or current and past set point, indoor, outdoor temperatures. We have access to occupancy sensor data. So that as well, and then what season it is and what the previous event is. So the data that I showed isn't just demand response changes, it's every automated set point change. So a lot of these are scheduled changes, or maybe changes due to some sort of smart recovery period. On the personal factors, we kind of took an initial shot at this. There's definitely room to improve what sort of personal factors we used, but we considered the average day of the week that the occupant overrides, the time of day of the average time of day of this person's overrides. Are they more likely to increase or decrease the set points during cooling seasons? And sometimes we found that there's actually kind of two different types of behaviors. Occupants sometimes will essentially override immediately, as if they were able to predict a scheduled change. And I'll even notice this at home. I can hear the thermostat click, and then I'll get up and go override it. So there's some that are doing it instantly, and then some that do it over more of what we would expect of the room temperature changes and they become uncomfortable. So we try to kind of classify those two different cases for that person. And then those are fed into the different models. So thanks for the opportunity to explain that more.
Okay, so you mentioned in your presentation that you have 100,000 thermostats that you looked at.
Yep.
And are these around the world, or are they in the US?
Around the world, but primarily in the US. I would say, just spitballing, about 70% of them are probably in the US.
So how did you account for environmental conditions in this range of areas? For example, weather conditions and various geographical locations.
So we did consider both, we classified it by seasons. So all analysis was separated by heating and cooling seasons. That behavior would be different in each one of those. And then we considered outdoor temperature and kind of the everything that we could imagine we sensed. We didn't specifically separate the analysis yet, at least by climate zone. But that's definitely an opportunity for further analysis.
Okay, I'll put a question here again back to Sarah Crosby from Carol Pendersky. Could you repeat what was the difference between the two databases, methodology of data collection as well?
Yeah. So like the main difference between the two methodologies, like we try to repeat and follow the same methodology. The main difference between the two data sets are that the first one is old. It's 17 years old. So that was the main purpose of repeating it, to have a recent data set. Our data set is only in Canada. The first one is across Canada and the US. We try to have like variation in the seasons. So we collected some data in spring and summer and winter, and we're planning to collect more in fall. The first one was mainly in summer and spring times. But in terms of methodologies, like data collection.
You want to turn your camera on, Sarah?
Excuse
Can
me?
you turn your camera on if you want, or just carry on, please?
Oh, yeah, sure.
Okay. So you're saying about the different data sets.
Yeah, so in terms of data collection, we try to follow the same methodology as much as we can. So we collected IEQ data from each workstation like they did. We try to use the same sensors, but we couldn't use the same exact sensor that they had.
Okay. So we have a question here for Simona. Simona, the question is, when using ICT to change behavior, how do you think the behavior change recommendation should be generated? Is it the computational algorithm behind these recommendations or something else?
Yeah, so at least what we are experiencing in our tool, the way we're providing behavioral change suggestions to the users is through gamification. So we're trying to use these gamified features that are contextual, of course. So we do have a full deployed sensor networks in the homes that we want to use as experiment. And when we provide feedback, for instance, more tailored information, we try to keep them as targeted as possible. So also in terms of providing actionable suggestions just when the users are, for instance, interacting with that specific control system, try to be realistic as much as possible. So don't ask to, for instance, open a window if it's not reachable at all, and of course being as timely as possible. There is for us the biggest challenge in being timely when you want to develop a real-time feedback system to create behavioral change through games. Which we know it's very effective, but of course it deals with a lot of barriers in terms of time and technology. Yeah.
Okay, there's also a following question to you from Andreas Wagner. The question is, are you also planning to give people the opportunity to interfere if they are feeling uncomfortable with your settings?
To give people possibility to interfere, what does it mean?
To change the settings.
Okay. Well, if the question is related to the experimental settings in the office, in our case, no. For the moment, we don't want them to interfere with the temperature training and with the lighting. So for the moment, we're keeping the experimental stable. So we want to get as much feedback as possible by keeping a control sample. And then by providing them the opportunity to provide just feedback, not a possibility to have actions, we want to tailor the curve of the temperature settings accordingly, and then reevaluating their feedback after.
Do you think that is representative of the actual situation if you don't give them an override?
Well, that's a key point. For the moment, we want to try to have a stable building management system to understand which are the limits. The second stage will be eventually giving them the possibility to, for instance, coming back to a fixed temperature during the whole day. But now our goal of the experiment is to test the hypothesis that this temperature training automatically generated by the building management system is indeed more effective in terms of satisfaction and productivity.
Okay, Fillipo, I've got a question to you. I know it's a very short presentation. What are the future plans for the work? How are you going to take it forward?
First of all, for sure, we need to validate the means of virtual reality in a way that is integrated with other methodology of monitoring the reliability of the instruments. And if it works, we want to find other triggers able to give placebo stimuli to the subjects.
For Yimin again, the same question. I know you had a lot of modeling that you're doing in your presentation. So where does it go to practical outcomes?
Sorry, Professor. Sorry, Professor. You were muted at the start there. Could you just restate that question?
Hello, Yimin. Did you hear the question, or shall I repeat it?
This is for me?
Yes.
Oh,
so,
I didn't get the question. I'm sorry.
Okay, so the question is, you have shown so many future plans for modeling and data analysis. How would that be taken forward to a practical applications, let's say in offices and things like that?
Yeah. So I think at this moment, though, the focus is still very much on the comparison between IV and the in situ in order to ensure that we find ways and parameters that we use measuring human building interaction, the IVE, are reliable in situ scenario. So that is the first step. Once, I mean, based on this initial study, we probably have more confidence than before. At least I have more confidence than before that if we well control the virtual environment, it could be a very good environment where we can study. We could have opportunity that we wouldn't be able to have in the real environment. But for the next step, I think people are really interested in, whether human being interactions that we observe in the VR environment is reliable, not just the sensation, right? So not just the psychological responses, but also behavioral responses, whether such behavioral responses are reliable. I think that is the next step that we'll be focusing on before I think we can actually talk about the practical applications of VR environment.
Okay, that's really great. So we still have 132 participants and 10 minutes to go. Anybody else wishes to ask a question?
It seems that moderators can't ask questions, or panelists can't ask questions through the digital system. So if you don't mind. You
can ask a question because you are a panelist.
Okay. Okay, I'll just ask a question the plain old way and just shout it out. So I have a question for Matteo. I love the results, and it's really interesting to kind of see your laboratory experiments versus the data from the field that we're analyzing. And I'm just wondering, I'm sure you'll do all sorts of wonderful multi-regression analysis later on, but do you have kind of simple kind of RMSE, or like what is your ability to kind of predict when a person might override? It looks like you're kind of, people might override anywhere from instantaneously to up to 2 hours later, which is kind of what we're seeing in the field. Have you tried to quantify that at all?
Not yet. That's of course a problem. To just decide when people, because as you see, it's very different. There are people that just react like 2 minutes after the ramp is start and they stop the button. So like they can predict actually the change in the slightly change in the temperature. And there are others that last for like way after. So that's the point, and it's no, not yet. Sadly, not yet. So it's something that we have to investigate in. Yeah.
I guess a question for everyone and all the other panelists who are doing laboratory experiments, whether you're measuring noise level and airflow, if they're using those as kind of preliminary triggers in not actually detecting thermal comfort, but they just are uncomfortable due to airflow or noise.
Yeah, I mean, we didn't measure actually the sound, so that's but we the measure it, but we have the questionnaire about it. So we still have the perception of the people, and the things that people were allowed also to press the stop button for not thermal stimuli, but we just go on until they press this button for thermal stimuli. So they can be that at the end they press for thermal, but there is also some visual problem. So that's also another point, that we can integrate both of them. So to understand if the visual or the sound or air movement has some interaction with the actual temperature variation.
Nice.
So we measure all these things, but we stopped the experiment just when the person was uncomfortable for the temperature, because that was our aim, let's say. But we still have all this information.
Yeah, great.
Do you want to respond to that as well? Perhaps, Michael, you may repeat the question for Sarah. And
yeah, for either Sarah or Yimin, just if you're measuring kind of the sound and the airspeed associated with the HVAC system that you're using in the laboratory tests.
Well, in the chamber, we don't measure them particularly, but we actually rely on the control system to maintain these two parameters. But we don't collect the data for those two parameters.
Yeah, for us, we actually measure for each workstation the noise levels and the airflow for each like desktop, and we have included these metrics to infer the probability of thermal comfort given these parameters. Yeah.
Thank you.
Okay, so I've got a specific question that just popped up from Farouk Dizizadeh, and it's for Matteo. Could you expand a bit more on your experimental conditions? For example, how long participants interact with the test bed?
Sorry, how long participants interact with the test bed, with your experiment? Okay, we had, I can perhaps maybe we share maybe screen. So can you see the screen?
Yeah.
Okay, so we start the experiment. The participant entered the cell at 8 a.m. and then it has 30 minutes for acclimatization. And then after that, until lunch, there was the experimental time. So in that period, we had the experiment itself. And then after lunch, same procedure. So 30 minutes of acclimatization and then the ramp. So in this time, we got some also questionnaire. And then, for example, the stop questionnaire depends if the person actually pressed the stop button. So we got that if the person was decide, let's say, to interrupt the experiment. If not, we just continue until the end of the experiment itself. That is 180 minutes, plus the 30 minutes of acclimatization, but that is a stable temperature.
Okay, and I think the question that came up now, which is the sort of question the chair should always ask at the end of the session, which came from Myra and Ray, to everyone who presented today: how do you feel your research can relate to one another? Who's going to take it?
Well, let me, I guess, let me start. I think my interest is, for example, right? So my interest in really understanding the capability of VR environment to support design engineering, especially for the building performance. But you know, many of the information that you guys presented, in my mind, I start to think whether it is ever possible for me to study in a virtual environment. What's the benefit of doing that? These kind of things. I think that's a I can see those kind of connections between, you know, different studies, especially the different studies with mine.
Yeah, yeah, absolutely. I can resonate with what you just said. For instance, in our experiment, especially for the dynamic lighting, we would definitely benefit, for instance, by using VR environments that could change those settings and then providing some tools to the users to provide feedback. And I'm also very interested in the possibility of using VR for assessing productivity when changing this dynamic environment, not only assessing increase in health, but also indeed productivity, which is a very important topic for us as well.
Okay. Anyone else?
I'll just follow up on my kind of question for Matt. I asked because I thought our research was highly related. He's working on data in a laboratory experiment while working in field experiments. And I think everyone here is really trying to understand the relationship between the occupant and the control system. And so I'm more of a controls person than an occupant human behavior person. So I'm really looking forward to kind of incorporating all of these into how we can really use these to help balance out the grid and increase renewables on the grid.
Okay, I've got a question now. We just came on from Yepa and Leo for you, Dr. Kane. He's wondering what kind of occupancy information did you consider in your study? Is it a binary variable like occupied or not occupied, or is it detects the number of occupants in the space?
Yep, so it does not detect the number of occupants in the space. So the Ecobee thermostats each thermostat has an occupancy sensor in it, and then people can buy external occupancy sensors to place around their house so that it can help balance the temperature throughout the house. But these are just simple passive infrared sensors, which are known to be kind of have very large errors. So we've actually engineered our analysis in a way that when we're considering the behavior part of it, we're only considering when we can detect that the person was in the space the entire time. Because the sensors are very rarely give false positives, but they very often give false negatives. And then when we're looking more at the controls, we want to be able to detect, we want to be more conservative and say, we want to say if someone will override. And for someone to override, they have to be in the space, but they might not always be in the space. So in that case, we'll only detect if a single instance of occupancy is detected. So, and then houses have anywhere between 1 and probably 5 occupancy sensors on average. Kind of the typical is probably just 1 or 2. So there's a lot of kind of dead space from these passive infrared sensors. So there's a lot of times where there's false and negatives, and we're trying to include that knowledge in our analysis.
Okay, last chance for a last question. Anybody else want to ask a question? Panelists could do that. You've got about 1 or 2 minutes if you wanted to ask each other a question, if you're willing to do that. Otherwise, we can close the session. And your offers? Okay, looks like everybody had enough from Zoom. So what I wanted to do is to just tell you something which is quite important. We still have 133 participants here. This session will now close. So the next session will be chaired by Ben Anderson, which is Occupant-Centric Building Controls. You will need to press on that session link for Zoom to come back on again so that you become part of the attendees or the presenters. But what I would say that the presenters should really start doing it now. And the rest of you, if you can wait for 5 minutes, please, so that we can start again on time, about 13:25 UK time. Okay, I hope that's clear. Session will close. Presenters, please go up straight away. The rest, please wait for 5 minutes. I enjoyed it. Thank you very much. And
thank you.
Thank you.
and Andreas Wagner said to applause to all the speakers and the audience. Can you do that live? Clap, clap. And for me.
Thank you everyone.
Thank you.
Thank you, and see you again later. Thank you.
Bye.
Bye for now.
Thank you.